Hello, my name is Kevin Drong with NanoSemi. Today we are showing one of our latest products development featuring ultra-wideband LTE advanced linearization for a wide range of power amplifiers, tested up to 100 watts average power, which is well suitable for the cellular infrastructure and 4G, 5G macro cell base stations. So here we have customized the FPGA of the analog devices transceiver evaluation platform to include our own digital predistortion, press factor reduction, and adaptation in its transmit and observation receive data path, making our DPD demonstration platform operate seamlessly with the analog devices and Xilinx infrastructure. Our solution goes beyond linearization and provides advanced features such as signal chain health, spectral, and EVM monitoring with no complex calibration. A general-purpose mini-circuits wideband amplifier is chosen as the driver between the 450 MHz bandwidth transceiver and the power amplifier, because we are going to analyze two power amplifiers side by side at two different carrier frequencies, namely 2550 MHz and 3500 MHz. There is two parts to this demo. The first part highlights an integrated two-stage gallium nitride power amplifier designed for metro cell base station application with a target 5 watts average power at the device output. Incorporates a Doherty final stage, delivering more than 40% power added efficiency with a gain of 36 dB. This module is 50 ohm input-output matched and also is compact in a 36-pin 6x10mm plastic surface mount package. The left stack of power supply is used to bias the entire module, including a drain voltage of 28 volts. The demo starts by loading 6 different carrier configurations to the DDR memory. We can then either use the ZC706 push buttons or my laptop to switch between the waveforms. With the push buttons, we actually have the programming ability to either bypass the linearizer block or to interrupt the adaptation. My laptop is also being used to automate the key size signal analyzer for properly configuring the ACP measurement application as we go through different waveforms. While examining the performance at 5 watts, we begin with transmitting 8 20 MHz component carriers to attain a total transmission bandwidth of 160 MHz, and then we will gradually decrease the bandwidth to 80 MHz. It is worth mentioning that throughout the measurements and the demonstrations, the output efficiency of the power amplifier is maintained to be 40% or better. The next waveform consists of 6 20 MHz component carriers to occupy a total instantaneous bandwidth of 120 MHz. As you can see that the moment we enable the linearizer, we can quickly achieve to 50 dBc or better. The third waveform consists of 5 component carriers which occupies a total transmission bandwidth of 100 MHz. The remaining 3 carrier configurations consist of 4 component carriers. Each of them occupies 80 MHz, except that we will park the carrier at different center locations. The next one actually parks at the center frequency of 2550 MHz. Then we will slide this carrier configuration by another 20 MHz, centering at 2570 MHz. For the next 50 seconds, we will simulate the dynamic traffic by switching the waveform every half a second. We will go from 120 MHz to 80 MHz and change the waveform rapidly. It is important to note that as we hop between different carrier configurations, no disruption in RF spectrum is observed, and hence we maintain a very good performance throughout the dynamic testing. This concludes part 1 of the video, and for the next 2 minutes we will actually power cycle and reinitialize the boards. The second power amplifier is an integrated two-stage wideband symmetric Doherty from 3400 MHz to 3800 MHz. The linear gain is at least 25 dB with a power efficiency around 30% at 2 watts average output power. We began the testings by looking at 3 different 200 MHz carrier aggregations. The first waveform consists of 10 components carrier to occupy the entire 200 MHz spectrum. Next, we will be looking at 2 20 MHz component carriers placed at very far away from each other. So the total distance we're looking at remains the same, 200 MHz. And you can see that with linearizations, we have no problem linearizing the power amplifier down to 57 or better dBc in ACOR. The third waveform we have is based on 4 component carrier where we place 2 of them very far away from each other. In this case, we can see that linearization maintains a very good performance, at least 50 dBc or better. Last but not least, we want to simulate the dynamic traffic by pushing the ZC706 buttons rapidly. Here we have preload 4 different waveforms to the DDR memory. So we are starting with 10 component carriers and then reduce the number down to 6 to 4 and eventually with 2 20 MHz spaced at 200 MHz apart. By looping through this different carrier configuration rapidly, we can show that there is no disruption in RF spectrum. And we can more or less maintain 50 dBc or better linearities for various 200 MHz test cases, while operating the power amplifier at 2 watts RMS. I hope you have enjoyed our PA agnostic DPD solution. Thanks for watching the video. For more information, please visit us at www.nanosemitech.com.